Hello everyone, I hope you are doing great. In this tutorial video, I want to talk about generation rate in perovskite solar cell that you can expand this example to other perovskite, to other solar cell material, for example CIGS, CZTS, silicon, and cadmium telluride, and every type of solar cell that you want to work. As you comment in the previous tutorial, some of you talk about 3D generation rate, and I think it's better we start from 3D generation rate modeling. In the COMSOL application libraries, you can find a 1D generation rate that, see this example. In this example, you can see the generation rate was calculated from Beer-Lambert law as a simple rules for one dimension problems. And in this tutorial, I want to do some simulations for calculating the generation rate, absorption of each layers, and reflectance of each layers, and also transmittance of each layers. Please subscribe my channel and let's start. Okay. As you can see, I've installed the COMSOL 6.1, and you can download it or you can buy it from the COMSOL Multiphysics sites. You can use a model wizard or blank model. It is arbitrary. I use a blank model for simplicity. Add component, I use 3D component. Okay. Also in the physics, I add physics in the, it's better go to radio frequency. We must use EWFT physics, and I must go to wave optics and use electromagnetic waves frequency domain EWFT physics. I just double click it on it, or I can add to component 1. Okay. Let me also use a study. I can use a study here, frequency domain. By double click you can add it. You can see the frequency domain. I close these windows. I go to geometry. I click right on it. I use block. We have two options when we want to create a geometry. We can write the exact values of the geometry, or we can use a parameter values. I use a parameter values, width, depth, and height. Okay. I define the widths. For example, 350 nanometer, and depths also I can use the previous value, and for height I can use HAU plus HTIO2 plus HPSK plus H spiral plus H, for example, AUTI, the perovskite spiral, FTO, and H for air. Okay, I use parametric definition for the height of our cell's height and height, excuse me, and I define each one of them separately. For example, HAU 80 nanometer, HTIO2 50 nanometer. Don't worry about the values. These values are extracted from valid reference. .300 nanometer for perovskite, spiral is 200 nanometer, can define H air long as a LDA max, and we can parameter LDA 0, which means the wavelength that we want to use in electromagnetic wave. It's from, for example, 300 nanometer LDA mean. Also can choose this value, LDA mean, LDA max. It's related to this equation that you can see, the cutoff wavelengths for the absorber layer. As we know, the band gap of perovskite can be varied, but the perovskite that we have used here has a band gap of 1.55 electron volt, which means the cutoff frequency is about 820 nanometer or lower, and I use a lambda max 820 nanometer. Okay, and H air, I forgot to add HFTO it's equal to 600 nanometer. Okay, as you can see, the height is black, which means you input all of the values correctly. I can copy these values. I use layers. I do the position of layer from the bottom to top. For the layer 1, I use HAU. I can cut the rest of them. I cut rest of them after TiO2. Perovskite, I cut them also. Spiro, I cut rest of them. HFTO, and for the last layer, it is not important to write the last layer, because the rest, the ends, as I talk about it, the end for the ends layer, you must input ends -1 layer name. Okay, I build all object. You can see the all of layer are appear here. Okay, in electromagnetic wave, I can, at first, it better use group by space dimension. It helps us to see domains and boundary in a separate windows. In electromagnetic, it better use a full field, and you better click all of the layers, and you have different electric displacement field calculations, for example, refractive index, theory, loss tangent, or the electric loss through Lorentz dispersion model. But as a common, we use refractive index, and we must input N and K, the real and imaginary part of the refractive index. We define at the end, in the boundaries, I must define the boundary condition. For example, I use a perfect electric conductor for the AU material. For example, as you can see, we must define the X and Y boundaries. For the X, I use a 2 direction of X, perfect electric conductor, AU X, and also it will be defined at the final the Y values. Okay, and AUY. But before removing the all layers, we must choose periodic conditions. Periodic condition in X direction. I use in X direction, which means these surfaces. I must click in all of the surfaces of the layers except of AU, because we consider it as a perfect electric conductor, that we know the AU or gold is metal contact and is it can be considered as perfect electric conductor. Okay, let me click on it, the X directions. Okay, also I can duplicate it. I can use rename Y. I remove them and I consider the opposite direction in Y side, in Y side of the geometry. Okay, as you can see, the Y values of the Y direction of AU is considered, but you can see the bottom and top also was considered, but don't worry about it. We must use a scattering boundary condition. The first, that means the light, we want to simulate a light illumination from the top. Use incident wave given by E field. We can define E values, the amplitude of electric field by E character, and use 0 for incident wave direction, and just use a KZ, which means the wave direction in this direction, but the E in X direction. Okay, we define E or electric field in the definition in the following of this tutorial. I duplicate this, and for this I remove the top and I select the bottom. I use no incident field. Also, please consider that the light is the plane wave here. You can modify to cylindrical wave, spherical wave, but it's related to laser or some filtered light. Okay, but here we want to simulate AM 1.5 global spectrum that is considered as plane wave. Okay, let's check the electric conductor, perfect electric conductor in the Y direction. As you can see, the Y is selected automatically and the other surfaces was removed because they selected in the following conditions. Okay, let me go to definitions. In the definition, I can use variables. In the variables, we must to define the parameter, the variables that we want to simulate. For example, generation rate, total generation rate at each wavelength, absorption of each layers, absorption of total absorption of device, total reflection of device, and every optical parameter that we need. Okay, let me start the optical. As we know, we can write E as two multiplied by I multiply by epsilon 0 relative conductivity of vacuum C const we must define I. The I is the integrate of phi am LDA 0 LDA 0 to LDA 0 plus step. It means you do your integral in phi am, and we define phi am the flux of am 1.5 global from LDA 0, which means the initial wavelength, to one step forward LDA 0 plus a step. Let me choose the phi am as phi am LDA 0. For definition of this function, because as you can search in internet and find the Excel file of AM 1.5, I can use interpolation. Previously I provided this value. I can copy and paste here. Okay, here the name of variable is not LDA 0, it means nanometer, and the function let me check the function. Yes, it's okay. And the name, we must use the exact name of phi am for the function name. And also the label is arbitrary, just for definition of AM 1.5. You can see the black color. Oh, it's mean I don't know why integrate, the step is not defined. Let me define the step function as a parameter. Let me check step. I can define a step as 10 nanometer, and I go back and check the color of these properties. Epsilon 0 must be defined. Let me define epsilon 0 in parameter. Epsilon 0 is equal to, let me check the data, 8.85, 41, E minus 12, F per meter. A farad per meter, it is the unit of epsilon 0. Excuse me, F per m. So, okay. And excuse me for that. Here we forgot use 1 to 0.5. We must divide this value, and now it is right. Let me show you by the formula. As we know that the intensity I is equal to 1 divided by 2 epsilon 0 C square of E. Okay, just by writing this equation, simple equation, we see the E is equal to 2I epsilon 0 C constant per square to 1 divided by 2. Okay, and let me, okay, for G total, it's better for G total. You can see the references. I will provide the references for you. Just comment to me if you need reference, because I cannot put the link, but I will provide you the name of paper. It's better to see the exact reference of this equation. For G total, we can use epsilon multiplied by the absolute values of EWFT norm E square, and what For the epsilon, let me define the epsilon. It's equal to 2 multiplied by n k plus epsilon and nk is defined by EWFD dot KA KI ISO plus multiplied by EWFD dot N ISO. Okay. Let me check it. Okay. This value is related to, let me check with you, nk, which means the n multiplied by k. Use control F, and you can control V. You can find the variable. You can use equation view, and you can use OK. Let me control F again. Okay. In equation view, you can see EWFD KIXX or ISO. Let me go to node. You can see the refractive index, imaginary part, isotropic value, just by using ISO. When you had material with isotropic or non-isotropic distribution in space, the NOK in different direction will be different. But here our materials are flat and also are isotropic, and we can use isotropic K. Okay, let me continue. Okay, for the material, I've provided previously the material data. Let me copy them, and I will tell you how you can. I copy them, and I paste multiple items. Okay, and you can see the data of the material, for example N and K. And I don't know why. Oh, excuse me, for NK epsilon, I forgot to use epsilon 0 here. And for this, the h bar const must be h bar const, as you can see. Okay, the total generation can be calculated here, and you can see the unit is correct. Please, in each steps of your simulation, check the unit of your variable. It can help you to understand did your simulation correct or false. Let me continue. Okay, well, for scattering boundary condition, I go back and then check the values. You can see the black color of these variable, which guarantee you use correct formula for considering the electric field. Also, for example, absorption of FTO or perovskite. Here for perovskite, we can choose abs PSK. I use abs PSK. For perovskite absorption, we must write the code that, let me choose abs. I will complete this, but let me choose the non-local coupling. I use integration for the domain. As we know, here we have perovskite. Let me check it again. Perovskite was 300, Spiro 200. It is perovskite. Okay, and it is perovskite int up 1. Okay, it means, let me to define it. When you use this operator, it means you have integrate on this bulk, which means you have integrate of dx, dy, dz, and you can write your any function here and you can integrate on it. Okay, I use int of 1. Int of 1 to do an integration on EWFD dot QRH multiplied by I divided by I multiplied by W cell multiplied by depths. Excuse me, let me check the widths and depths for widths and depths. As you can see, it is correct, and also we must choose an it's okay. Okay, for understanding this formula, I can write it here for you. It means the integration on EWFT QRH, or let me do a simple QRH divided by I multiplied by width W multiplied by D, which means depths, all of them, dx, dy, and dz. This is the absorption. Why we call this absorption? Because QRH, it means the dissipation power. Let me find it for you. You can see QRH here. It means resistive losses, which means the absorption of the light into a bulk material. That means the light was attenuated and was absorbed by the mentioned layer. Okay, we can see the absorption of perovskite for the for example transmission. I can choose T PSK, and let me choose this again, but we must remove the int up, and we must use NPOR. Okay, we must use integration on the back surface, on the bottom surface of the perovskite, because for the transmission you must see the light that was transmitted from the bottom surface layer of perovskite. Let me show you. Here we have int up 2. I can select all of them. I can use transparency. I can also I must choose boundary. Let me to click on it again. I use the backflash, and you can see the geometry. The surface 9 is related to perovskite. Let me remove all of them and use geometry 9, which means the exact geometry that we need for the int up 2. You can see the transmission, and also for reflection. Let me, for PSK, I can use For reflection, we can use this simple equation 1 minus abs psk minus t psk. Okay, we have three variable: absorption, transmission, and reflection for perovskite layer. Okay, we go to study 1. We use parametric sweep. In the parameter name, I add LDA 0. I can variable it by using range function from LDA mean and step to LDA max nanometer, and also in the frequencies we must use F0. I define F0 as a C const divided by LDA 0. Okay. It's better also check these parameters. Okay. The F0 is black, which means it is readable in the parameters and materials property. For the final settings, we must use a mesh. The mesh is important. I use a user defined mesh. I click right on it. I use size, and also I use a free tetrahedral. For scale geometry, you can set them onto 2, 2, and 1, and also the size you can use finer, and also for this you can use finer. You can see the mesh. It depends on your system, it depends on your problem. You can use a different mesh. In study 1, at first you must consider this fact. It's better save your problem. Let me save it. I save it. I use a compute. I hope this will run without any errors. I hope this run. It's okay. It is running now without any problems, and it takes a time. It's based on your system configuration, and after the running of this simulation, we can plot the generation rate versus long LDA 0. We can plot electric field. We can plot transmittance, absorbance, and reflection of the perovskite layer. For other layers, we do the same method that I talked with you, and I hope by seeing this tutorial video you can to run any device configuration with minimum of errors. You can run it and take the related result that you wanted. Let me check the log file also. You can check your log file to see the number of degree of freedoms and the damping factor. Also, you can see the progress, the percentage of computation, the parameters of LDA 0. We are in 410 nanometer. Okay. For finding, let me show you the refractive index. For example, for FTO, I can plot it for you. You can see the N and K for FTO. Also, you can search in the internet. Let me show you one of the best sites for downloading refractive index of materials. As I know, refractive index .info is the best site for finding the material. You can also search in the tab bar, for example, CH3 PBI3. Okay, you can see the refractive index of perovskite. As you can see, this is a N and K for the perovskite, and you can download it by CSV or text or any data you want, and you can open it. You can download the data of NK for other material also. Just search in search bar in the top of this site. Okay, the run is completed now, and you can see the electric field result here. And also I can let me use a 3D plot group. Use a surface. In surface, you can go to definition and function. Let me choose a variable, for example G total G. You can see the generation for you can use parametric sweep and use different wavelengths. You can see the generation rate for different wavelengths. After that, you must sum all of these wavelengths together. After summing all of this wavelength generation, you have a total generation for using your semiconductor properties or electrical part to do your IV curve and calculate your efficiency, fill factor, short current density, and also open circuit voltage. Okay, let me plot 1D global and use the parametric. I can choose all solution, expression. I write the LDA 0, LDA 0, 0. I can choose a nanometer, and here we can use definition, functions, variables, use absorption for perovskite. You can see the absorption for perovskite. Let me show you. As you can see, we have the absorption from 300 nanometer wavelengths to 800 nanometer. You can see the higher absorption in the range of UV visible region, and we can duplicate this plot. Let me duplicate this plot for plotting reflectance and also transmittance of perovskite. This fluctuation in the figure tell us it's better to use a better mesh. Here it would better I used extra fine mesh to have the high resolution of spectrum, especially for absorption. Okay, let me choose other definition. I go to variables. I use for example T perovskite. It needs a little time for do the calculation. As you can see, the transmission is very low, as it can predictable because the perovskite is absorber, and we want to do the absorb light and not transmit the light. And also for the reflection, let me duplicate it. Okay, I can use go to definition in variables, the R perovskite. I use plot. And you can see the reflection of perovskite is also very lower than the absorption of perovskite, and these results are reasonable, and you can use it for your papers, for your project. And if you have any question, please feel free and ask me. You can do your comments in this below link of this tutorial video. Please subscribe my channel, press the ring button to inform the latest video of my channel, and also like this video and tell your friends, your colleagues to join to this channel. I'm going to provide many interesting video for you to interest knowledge and use your knowledge in your real life. And I hope I would help you to enjoy the science and knowledge in near future. Take care, have a good time, goodbye.